Assalamualaikum and hi everyone. We are now in the third subtopic, which is linearly independence. In linear algebra, the concept of linearly independence is refers to a set S. Let's say we have a set S, where S is a subset of a vector space V. V is a vector space and S is a subset of V. Bear in mind that S is not necessarily a subspace of V. Okay, so S is a collection of some vectors. Let's say vector V1, V2, Vt, etc. up to Vr. Okay, so here comes the concept of linearly dependence. If there is one element, one vector in the set S, let's say V3 is a linear combination of the other vectors, which is V1, V2, V4 up to Vr. Okay, if we found that V3, for example, is a linear combination of the other vectors in the set S, then that means V3 is dependence to other vectors, and that means the set S is linear dependence. Okay, so basically S is linearly dependent if we can find at least one element, one vector in the set S such that the vector is a linear combination of the other vectors in the set S. Okay, so you may recall what does it mean by linear combination that we have discussed earlier in the previous topics. Alright, so the opposite to the linear dependence is linearly independence. Okay, so refer to the set S again. S is said to be linearly independent. S is linear independence by the same concept that we have discussed earlier is when we cannot find such vectors V that can be expressed as linear combinations of the other vectors. So S is linearly independent when none of the vectors in S can be expressed as a linear combination of the other elements, the other vectors in S. Okay, linear combinations means that you may recall that if V is a linear combination of the other vectors, that means V is K1 V1 plus K2 V2 plus up to Kn Vn. So if we can write this equation, that means V is a linear combination of the other vectors in S. Okay, so this is the concepts of linear independence and linearly dependence of a set of vectors S. Now, how are we going to determine a set S is linearly independent or linearly dependent? To do that, we start off by writing these equations. We have this equation where the right hand side is linear combinations of vectors in S, and the left hand side here is the 0 vector. Okay, so look at the left hand side. We have K1, K2, Kr are any scalars, and V1, V2 up to Vr are vectors in set S. Okay, so we might question, does the values of K1, K2 up to Kr exist? Does the value of scalars K1, K2 up to Kr exist such that this equation is hold true? You may recall that whenever we have a homogeneous systems of linear equation, homogeneous systems of linear equation is whenever the parameter, the scalars at the right hand side is all zeros. Okay, for such systems of linear equation, the system there is a guarantee that the system has a solution where it must has trivial solution. The trivial solution here is K1, K2 up to Kr are all zeros. So this is guarantee that the trivial solution exists. However, the non-trivial solution, which is to the opposite of the trivial solution, is not necessarily exist. Okay, so we know that this equation has at least one solution, which is a trivial solution, and if this trivial solution is the only solution, means that we cannot have any other solution, we don't have a non-trivial solution, then the set S is said to be linearly independent. On the other hand, if there are some other solutions, means that non-trivial solution exists, okay, then the set S is linearly dependent set. Now we move on to our first example. In this example, we have to show that the set S, which contains V1, V2, V3, is linearly dependent. Okay, so since V1, V2, V3 are in R4, therefore S is a subset of real vector R4. Okay, recall that to show that S is linearly dependent from the concepts of linearly dependent set, that means if we write K1 V1 plus K2 V2 plus K3 V3 equal to the 0 vector in R4, then K1, K2, K3 is not necessarily the trivial solution. Means that we can find K1, K2, K3 such that they are not entirely are zeros. K1, K2, K3 not entirely zeros. Okay. One more thing to note that we have to identify the 0 vector in R4. So since we have R4 as the vector space, therefore the zero vector here is 0, 0, 0, 0. Okay, now we have to show that K1, K2, K3, which not entirely zeros, exist such that this equation is true. Okay. This is true. This is proven since we have found K1, K2, K3, where this is K1, K2, and K3, such that K1V1 plus K2V2 plus K3V3 equal to 0 vector. Supposed to be another component. Okay, so because of this, because we can find K1, K2, K3, therefore the set S here, this is S, is linearly dependent set. Alright, bear in mind that the values of K1, K2, K3, the non-trivial solution for K1, K2, K3 is not necessarily unique. You might end up to different values of K1, K2, K3. As long as they are not entirely zeros, then the proving of linear dependence is done. Okay, then we move to the next example. The same example to the previous one, but in this example, we are considering vector space of P2. Recall that P2 is a collection of all polynomial of degree 2. Okay, so now again, we have to show that S with P1, P2, and P3 is linearly dependent. Okay, and S is a subset of P2. Okay, where P2 is a vector space of polynomials of degree 2. So to show that S is linearly dependent, we have to show that there exists K1, K2, K3 that are not entirely zeros, okay, such that K1 P1 plus K2 P2 plus K3 P3 is equal to 0 vector in P2. Okay, so again, it is very important to identify the 0 vector in any vector space, here in the vector space of polynomial of degree 2. And as we have seen in the previous subtopic, the 0 vector for this vector space is 0 times 1 plus 0 x plus 0 x squared. So this is also a polynomial of degree 2, and this is the 0 vector. So we have shown that, okay, by finding the value of K1, which is 3, K2 is -1, and K3 is 2. That makes this equation is equal to the 0 vector here. Okay, therefore the set of P1, P2, P3, the set S of P1, P2, P3 is linearly dependent in P2. Okay, then we move to another example. In this example, we have to show that I, J, and K form a linearly independent set in R3. So now we have S, I, J, and K Okay, where I, j and k as given in the question, this is a subset of R3 and S is linearly independent set. Okay, to show that S is linearly independent, that means we have to show that if K1I plus K2J plus K3K equal to the zero vector, okay, then the only possibilities for K1, K2, K3 are all zero. We don't have any other values for K1, K2, K3 except K1, K2, K3 are all zeros. Okay, before that, again, we have to identify the zero vector in R3. Since we equip R3 with the standard addition and scalar multiplication, therefore the zero vector of R3 is 0, 0, 0. Okay, now we have to here is the proof. Again, as I mentioned earlier, we have to show that K1, K2, K3 are all zeros, are the only scalars, are the only solution for this equation. Okay, so to write the solution, to write the proof, we start by letting K1I plus K2J plus K3K equal to zero vector. Okay, and then we substitute the value of I, J and K here. So I, J and K, and we substitute the vector, zero vector, which is 0, 0, 0, and then we try to figure out, we try to get the solution, and we want to find the values of K1, K2, K3. Okay, then on the left hand side, we have this, okay, which is equal to the zero vector 0, 0, 0, and then we compare component by component. We found that K1, K2, K3 are all zeros. Since 0 is the only solutions, the trivial solution is the only solution, therefore I, J and K is I, J and K form a linearly independent set. Okay, and then okay, so we move to the next example. Again, we have a vector space R3, and we are given three vectors v1, v2, v3 as follows. And again, we want to show that the set S with v1, v2, v3 subset to R3 is a linearly dependent set. Okay, so again, to show that S is linearly dependent, we have to show that the values for K1, K2, K3 are not necessarily all zeros. To do that, we start by letting K1 V1 plus K2 V2 plus K3 V3 equal to the zero vector, and then we substitute the value of vector V1, V2, V3 here, and then we substitute the zero vector as the origin 0, 0, 0, and then we simplify the left hand side. We get this and then we compare component by component from the right hand side and then the left hand side. We end up to a systems of linear equations, and we want to solve the systems of linear equation because we want to know the possibilities. We want to know the solutions for K1, K2 and 3. Therefore, we solve the systems of linear equation to get the values of K1, K2 and K3. Okay, by using the coefficient matrix, the augmented matrix. We perform the elementary row operation to the augmented matrix. We have this RREF form, and then from this form, since we have one row that consists entirely 0 entries, that means this system has infinitely many solutions. You don't have to calculate the solutions for K1, K2, K3, because from this form of RREF matrix, we can conclude directly that the system has infinitely many solutions. So you don't have to give the solution. It is enough to mention that since the RREF form consists one row which consists entirely 0 entries, therefore the systems of linear equation has infinitely many solutions. It has non-trivial solution. Therefore, the set is linearly dependent set. Another example, again now the vector space is Pn of polynomial of degree at most n. We have n plus 1 vectors here. We have n plus 1 vectors here. Okay, and then we want to show that these vectors form a linearly independent set in Pn. Okay, so again, we start by writing K01 plus K1x plus up to Knxn equal to the 0 vectors. You may notice here that my first scalars is K0, and then I have another scalar, K1. Compared to the previous example, I always start my scalars with K1. But that's not a problem at all. It's just a symbol. You may use any other symbols as you like. Alright, so we have this equation. And then we substitute the 0 vector. Okay, where the 0 vector here is this polynomial of the degree at most n with coefficient zeros. All coefficients of all variables are all zeros. Okay, and then again remember that we want to compute the solutions. That's mean we want to find the values of K0, K1 up to Kn. Comparing left hand side to the right hand side by look at the coefficients of 1, the coefficients of x, and up to coefficients of xn. So let me explain this again. Okay, up at this stage, look at the this is left hand side and the right hand side. At the left hand side, the coefficients of 1 is k0, and on the right hand side, the coefficients of 1 is 0. That's why we have k0 equal to 0. Okay, and then again on the left hand side, the coefficients of x is k1. Okay, and the coefficients of x in right hand side is 0. That's why we have k1 equal to 0. And we repeat the same until we get the value of kn, where we found that the value of kn is also 0. That means it doesn't have any other solutions. The only solutions is the trivial solution. Therefore, the set is linearly independent. Theorem 3.5. This theorem gives us an alternative to show a set S is linearly dependent or a set S is linearly independent. If you can recall the concepts of linearly dependence and linear independence that we have discussed at the beginning of this section, then you may see that the contents of this theorem is similar to the concept of linear independence and independence that we have discussed at the very beginning of this subsection. So if you understand that concept, then you may found that the proving of this theorem is quite straightforward. Okay, so let's look at the contents of this theorem. This theorem says that set S has two or more vectors and it is linearly dependent. Okay, S with two or more vectors is linearly dependent if and only if. So we have if and only if statement. At least one of the vectors in S is expressible as a linear combination of the other vectors in S. Means that we may find at least one vector in S such that the vector can be written as a linear combination of the other vectors in S. Alright. This theorem is a if and only if statement. Therefore, we have to prove two directions. In the first direction, we assume that S contains R vectors, which is V1, V2 up to Vr, and the set S is linearly dependent. Alright. So we may recall that linearly dependence means that whenever we write the equation where the right hand side of the equation is the zero vector and the left hand side is the linear combination of all vectors in S, then we found that the solution for the equation, which is the values of V1, K1, K2 up to Kr, is not necessarily trivial. Which means we can also have the other non-trivial solutions for the equations. That means there exist scalars K1, K2 up to Kr such that the values of these scalars are not entirely zero, and this equation is whole true. Okay, bear in mind we want to show the existence of one vector in S, the existence of one vector in S such that the vector can be write as a linear combination of the other vectors in S. Okay, so from this equation, okay, before that I have to remind that, okay, we have many cases for the non-zero value of the scalars. The first case is K1 is not equal to 0. The second case is K2 is not equal to 0, or up to case R where KR is not equal to 0. Doesn't matter which cases we want to consider, the proving is followed similarly. Therefore, without loss of generality, we assume only the first case, which is K1 is not equal to 0. Okay. Since K1 is not equal to 0, therefore we are able to divide the left and right hand side of the equation with K1. Okay, we divide with K1 because K1 is not equal to 0, and we bring every terms in the left hand side to the right except the term for V1. So we end up to this equation, and we see that V1 is a linear combination of the other vectors in S. Okay, so the proving for the first direction is completed. In the other direction, we let that there exists one vector in S which can be expressible as a linear combination of the other vectors in S. Okay, again, there are many cases where the first case is the vector that we found here is V1. The second case is the vector here is V2, and up to case R where the vector is VR. Again, doesn't matter which case that we want to consider, the proving will follow similarly. Therefore, we say without loss of generality, we assume that the vector that can be written as a linear combination of the other vectors in S is the vector V1. Therefore, we may write V1 as follows, which is a linear combination of the other vectors in S, where the values of scalars K2 up to KR not entirely zeros. Okay, the values of the scalars K2 up to KR is not entirely zeros. Okay, then we are able to write this equation with the zero vector at the right hand side. Okay, and we found that the solution of this equation is not necessarily the trivial solution. Therefore, we have seen that we have completed the proof for the second direction by showing that the set S is linearly dependent. Therefore, the set S is linearly dependent, and therefore the proof for this theorem is completed. Okay, we move to second theorem. This theorem says that whenever we have a set of finite vectors, and one of the vectors in the set is the zero vector contained in the set, then the set is linearly dependent. Okay, the set is linearly dependent. So we S with finitely many set, and we found that one of the set is the zero vector. Okay, then S is linearly dependent. Alright, so let's see the proof. We start by letting S is a set with finitely many vectors, and one of the vector is the zero vector. Okay, therefore we write the zero vector as a linear combination of the other vectors. This equation is true. It obviously is true where we found that the values of K1, K2, KR plus 1 are not entirely zeros, and therefore the set S with these vectors is the linear dependence, because the solution for this equations is not just the trivial one. The solution, the non-trivial solution is exists. Therefore, S is linear dependence. So that complete the proof for this theorem. Now we are going to see some illustration on in this slide. We are going to see how we can illustrate geometrically a linear independent set and linear dependent set for two-dimensional Euclidean space. So let's say we have a set S with two vectors. A set S with two vectors. R2 is supposed to be R2 here. Okay, and look at the first picture. Whenever S is linear dependence, we have two cases here. Case 1 and case 2. Okay, whenever S is linear dependence, then it is either case 1 or case 2, where for the first case, when we draw V1 and V2 at the same plane, xy plane, we draw V1 and V2 at the same xy plane, and we locate its initial point. At the origin. We found that this V1 and V2 have similar direction, and they lie on the same line. V1 and V2. So this is V1, and the green one is V2. Okay, they both lie on the same line, and they have similar direction. And in the second case, again, these two vectors lie in the same line. However, the direction is the opposite to each other. Okay, in the second picture, the set S is linear independence. That means we are going to found that V1 and V2 do not lie on the same line. They do not lie on the same line. Okay, so this is how we illustrate geometrically a set S which is linearly dependent for the first picture, and linear independence for the second picture. Okay, for the three-dimensional Euclidean space, let us consider S with three vectors. A set S with three vectors. Okay, so we are going to have these two pictures. The first picture represents a set S which is linearly dependent set S. Whenever we draw these three vectors on a same space and their initial points at the origin, we found that these three vectors lie on the same plane. They lie on the same plane. You may see in this picture that the yellow region that we draw is one plane, and these three vectors lies on the same plane. So the vector is V1, V2, V3. However, for linearly independent set, three vectors do not lie on the same plane. Okay, where if you try to figure it out, it ends up to two plane. One plane consists only two vectors, and another plane consists of two vectors. Okay, so this is how we differentiate between linearly independent and linearly dependent set for two-dimensional equivalent space and three-dimensional equivalent space. Alright, this theorem also helps us to determine if a set is linearly dependent or not. Okay, so let's say, before that, bear in mind, this theorem is only hold true whenever we consider Euclidean space. Whenever we consider Euclidean vector space, that means R1, R2, up to Rn in general. So we have S consists of R vectors. All vectors are in Rn. Okay, if the number of elements in S is R. Okay, the number of elements in S is R, and R is greater than N. R is greater than N. What is N? N is the dimension of the vector space. So if we consider two-dimensional equivalent space, then N is equal to 2. Okay, so in general, if the number of elements in S is greater than the dimensional of the equivalent space, then S is linearly dependent. S is linearly dependent. So, for example, if we have S as 1, 2, 3, 4, right? So the set S has 3 vectors from R3. From R2, and R is equal to 2. R is equal to 3. Okay, because we have 3 vectors in S, and N is equal to 2 because we are considering two-dimensional equivalent space. We found that R is greater than N. Therefore, this theorem says that S is linearly dependent. Okay, you don't have to prove by using definition of linearly dependence. This theorem says that the set S is linearly dependent. I left the proof for you to to understand everything in detail. Okay. In the current slide, we are going to discuss a very special vector space. That vector space is denoted as C n minus 1 in bracket. Okay, this is a set, is a collection of all real valued functions which have n minus 1 derivative which has continuous In this current slide, we are going to discuss on a very special vector space. It is denoted as C n minus 1 in bracket, negative infinity, infinity. This is a collection of all real valued functions, which have continuous n minus 1 derivative on the set negative infinity, infinity. That means this set if we write in terms of this symbol, the bracket, the elements are f, where f is a real valued function and this is the n minus 1 derivative of f is continuous. On negative infinity, infinity. So we have set C. For example, if n minus 1 equal to 3, so okay, so we are going to have C 3 negative infinity, infinity, where the element of this set is any real valued function f with additional conditions, which is f3, the third derivative of f is continuous at negative infinity, infinity. So this is the set C whenever n minus 1 equal to 3. So example of the set. Example of the set C3, let's say gx equal to 4x squared. Obviously, g is a real valued function whenever g is from R to R. So g is a real valued function because the range and the codomain is in R, and the first derivative of g is ax, second derivative of g is a, and the third derivative is 0. So we know that the scalar function is continuous at any interval. So okay, we are going to see a subset of this vector. How to determine a set of this vector is linearly independent or linearly dependent. Okay, so we have n vectors. We have n vectors here. Okay, and these vectors, these functions are n minus 1 differentiable. Okay, that's mean f1, f2, up to Fn, they are all in C n minus 1. Let me change the color. Okay. Alright. So, there is a term called Wronskians of these vectors. Wronskians of this vector is the determinant. Okay, this means that this is a determinant of a matrix where the entries of the matrix is given by this. In the first row, we list all the vectors, and in the second row, we list the first derivative, and in nth row, this is nth row, we list n minus 1 time n minus 1 derivative of every vectors. Okay, and this determinant is called Wronskians of these functions, and it is denoted by Wx. Okay, this person found that if the Wronskian is not zero, it's not identically zero. Okay, it's not identically zero because the Wronskian is a function in terms of x, and the determinant, the Wronskian Wx, Wx is not identically zero, then we can conclude that the collection of these functions f1 up to fn form a set which is linearly independent on this vector space. So, whenever the Wronskian is not entirely zero, it's not entirely zero, means that it's not equal to, the function is not zero, it's not equal to zero, then the set S with f1, f2 up to fn, they are vectors, subset to Cn minus 1. Okay, S is linearly independence. Okay, to understand this, let's consider example. Okay, we consider this vector space, and we have f1 and f2. f1 and f2 is f1 prime and f prime 2 are both different, continuously differentiable, and the Wronskian of f1 and f2 is given by this determinant, which is equal to this function, and this function is not entirely zero. This function is not entirely zero because we can find some value of x. We can find some value of x such that the value of w at that point is not zero. Then the set S, which contain f1 and f2, are linearly independent. Okay, that the same goes to the next example. In this vector space, okay, we have to consider f1, f2, and f3, and we found that the Wronskian is not equal to 0 again, and then the vectors f1, f2, f3 form a linearly independent set. Recall that the theorem says that whenever the Wronskian is not equal to 0, then the vectors f1, f2 up to fn, these vectors form a set which is linearly independent. However, the converse is not true. That means if the Wronskian is 0, we cannot make any conclusion. Why? Because there is a counterexample where the Wronskian is 0, however, the vectors form a set which is linearly independent, not necessarily dependent. So this is the example. You may see the Wronskian is 0, but the vectors form a set which is linearly independent. Okay, so that's the end of this section. Thank you.